Well, I just figured out another way to get divorced. Keep working on Breakout. Never done an FPGA before, so this should be a good way to learn. The goal for the FPGA series is to get Breakout working and then create a circuit board that'll run in the cabinet. In this video, we'll go over the basics and build the oscillator divider section. I selected the Arduino 3.1 development board with the Lattice ICE40 FPGA, lots of pins, and fits nicely on a breadboard. I followed the instructions to download their free toolchain and drivers. Here you use your own IDE like Visual Studio Code and a command line interface to compile and upload. I soldered on pin headers, dropped it onto a breadboard, and connected it to my Windows development machine with a USB cable. The program we'll use to interact with the board is called APIO. Here you can see that it properly detects our module. This development board is not a panacea. We'll still need support circuitry to bring in switches and controls and to drive audio, video, LEDs, etc. The ICE40 uses 3.3 volt I/O, so we'll need to do some level shifting on the inputs by using 74 LVC 244s, which support standard 5 volt TTL inputs, but drive the required 3.3 volt signals. The Arduino itself gets 5 volts power from the USB port and has an onboard regulator to supply 3.3 volts. We can use a bit of current from the exposed 3.3 volt pin for our input translators, but not too much. The Arduino's outputs are 5 volt TTL level compliant, so we can drive LS chips directly. Verilog is supposedly the most widely used hardware definition language, so we'll stick with that. I made a folder for this project, and the first file we'll add is apio.ini, which tells the compiler which board we have and the name of our top module. You can use top or main or whatever flips your skirt up. The top module is kind of like a program's main, where everything is corralled together. Each section of code we build is considered a module, and just like in a program, we define the required modules, then instantiate them in the design. Modules start with the module keyword, then a module name, then a list of parameters in parentheses. You end the parameter list with a semicolon, then do some work and wrap up the definition with the end module keyword. This syntax feels a bit like Pascal and C had a bastard child. The parameters of modules are called ports. You can consider them like wires bringing signals in and out. The top level module is special in that its port parameters connect to device I/O pins, and the mapping in this framework is handled by lines in a special PCF file. The mapping syntax is simple. Use the set I/O keyword followed by a signal name, then a GPIO port number. The compiler automatically figures out if you're using it as an input, output, or as a bidirectional line. The GPIO numbers here are logical. They are not physical Arduino or FPGA package pins. These numbers specify the logical general purpose I/O port on the FPGA and are nicely marked on the Arduino silkscreen. The signal name itself must also exactly match a top module port name. There are some specific pins that connect internally to what they call global buffers. These can give external clocks or lines easy access to special high-speed routes within the chip. This is not too important in this design because our oscillator is not that fast and we divide it down before using it anyway. But we'll bring our external clock into global buffer GPIO 20 for good measure. There is an onboard 12 MHz oscillator that we can tie to GPIO 20 by shorting these pins. We'll look into using that later. The first thing we need to do is breadboard the 14.318 MHz oscillator and bring that into GPIO 20. We'll need a 74 LS240 for the inverters, a 74 LVC 244 for input level shifting, and our normal set of passives. Next, we add a mapping to the PCF file to bring this signal into our main module. Well, let's build our first section, the oscillator divider. I'll create a new file for that and add the module framework. I'm making up my own convention of prefacing our module section definitions with mod. Looking at the schematic, this section takes in the oscillator signal and puts out clock in CKBH. Internally, there's a 4-bit binary counter and a couple of gates. Right away, we'll need to make a 74161, so let's create a new TTL file to corral all of our chips. I'll preface definitions in this file with TTL since we can't start a name with a number. We'll use pin names found in the breakout schematics and add the input and output wires. I like to put the inputs before the outputs, but you can mix them up if you want. I'll use one industry convention of adding the _n suffix for negative active logic lines. Since we have a 4-bit wide chip, we tell the compiler that data in is a 4-bit array of wires by using square brackets and giving the MSB to LSB. For the Q output, we need to use the reg keyword because the value is held in a register. You can consider that a reg is also a wire, but with special storage properties. Okay, we've defined the I/O ports for our counter. Now we need to do some work. The assign keyword simply says to drive the wire on the left from combo logic on the right. Here we're telling the compiler that TC is driven high when all output bits are on and the CET input is high. This notation does what's called a reduction AND. The result is 1 when all bits of Q are on. The next thing we need is an always block. Always blocks wait for something in its parameter list to change before doing stuff within the block. Within the block, changes can only be made to reg values, and you cannot use the assign keyword. Any changes made within an always block are scheduled to update simultaneously when the block ends. The 74161 has synchronized load and step functions and an asynchronous reset. The load and step functions operate on the positive edge of the clock, so we add the pos edge keyword for the clock signal. To detect resets, we also add the neg edge keyword and the MR signal. We'll therefore enter this block when the clock rises or when the master reset line falls. Now, just like in a program, we can check and do stuff with if-then-else statements. The first thing we'll do is check the reset line because it overrides everything. If the line is low, either it just went low or was low when the clock rose, we set the registered outputs to 0. This operator schedules placing the right side value into the left side register when the always block ends. For constants, you start with the bit width, followed by a single quote tick, then the radix, then the value. I'm using binary, but you can also use hex or decimal. You can do logical checks in many ways, depending on your preference. These statements are equivalent. If we're not in reset, the only other way we got in here is if the clock rose. We next check if the load line is down, and if so, load the register with a preset data value. If load was not down, we finally check if the count enable inputs are both up, and if so, step the counter. Save that and back to our oscillator divider to define the I/O parameters. We built the oscillator itself off board and we're just bringing in the 14.318 MHz signal. This module then puts out the clock and CKBH lines. Next, we need to instantiate one of our 74161s by specifying the module definition name, then give it an instance name, followed by the parameters. I like to copy the parameter lines from the module definition so I don't miss anything. Pare that down, then fill it in. You use the dot operator to specify the module port. Then in parentheses, you say which wire or wires you're connecting it to. We wire the oscillator line to the clock, then pull the master reset, CEP, and CET lines high, and load the preset data with 2. We finally get to the point where we need to wire up the Q and TC outputs, but there's nothing to wire them to. Here we need to create loose wires to hold these values so we can use them elsewhere. I like to define loose wires right above the driving module for easy reference. This Q wire here does attach to registered outputs in the 74161, but we don't need to use the reg keyword here because the 74161Q output is already defined as a register. We're just connecting the loose Q wire to it like a jumper. You'll see that we have Q and Q. These names don't have to be the same, but you'll often see wires hooked to similarly named ports when it makes sense. They are different though. The .Q is our 74161 module port, and the second Q is the loose wire. The only 74161 port not hooked up yet is the load line. Here I ran into my first dilemma. Do we make individual gate modules and instantiate them with the proper breakout site names, or do we reduce and simplify? Here we can do a few things. The worst thing we could do is define an entire 7404 chip with 6 inverters, then instantiate that somewhere and try to hook wires to it across multiple sections, wherever they're used. Another way would be to define single inverter gate modules and instantiate just one of those. This is fine, but requires an intermediary wire for the output. Or we can simply invert the TC wire we already have, effectively collapsing the individual breakout gate into the design. My preference is the latter, but with a comment on which gates are represented or replaced by the simple logic. We'll see this again in a second. The counter is hooked up, and now we need to derive our 2 module outputs, clock and CKBH. CKBH is easy. We can simply assign CKBH to counter output B, like so. To get clock, we need to AND outputs A and B. Once again, we can define an AND gate module, but I prefer a reduction with comment, like this. Much cleaner in the grand scheme of things and generates the same underlying circuit in the FPGA. So the oscillator divider's done. Let's go back to main, instantiate that, and hook it up. You can see now why I prefix the module definition with mod, so I can use the section name as the instance name. We'll hook the oscillator port to the oscillator GPIO port defined in the PCF file. We can test this section's outputs by temporarily hooking the clock and CKBH lines as some main port I/O pins and throwing them on the scope. To compile and upload, we open a command prompt, then set the directory to our project folder and issue the build command. Next, we issue upload. Alright, we've got our unbalanced 4.09 MHz clock signal and CKBH. That was a lot of work for just this, but we needed to put our basic framework together, so I think it's a good enough start. In the next session, we'll build video counters and sync circuitry, then do the borders and flip logic. At least enough stuff to get something on the screen. Thanks for watching.